The concept of a percent is among the most widely used mathematical construction found in real-life applications. For example, percents appear as a sales tax when you make purchases and as tips when you eat at a restaurant. They also appear as interest when taking out a car loan or when using a credit card. You see them when reading and interpreting scientific information and materials. They're important to medicine and budgets. You will also see them when working with probability and statistics. The word percent means for each 100. It establishes a proportion relative to 100 objects. For example, an 8% sales tax means that you will pay $8 for each $100 of goods you purchase. This means that if you spend $200, you will pay $16 in taxes, and if you spend $1,000, you will pay $80 in taxes. This works out easily when working with multiples of $100, but what happens if you need to compute the sales tax for a purchase of $632.74? To handle this situation, we need to establish a general relationship for percents. The primary formula we use for percents is percentage equals part over whole times 100%. To use this formula, we need to make sure we understand what each word represents. The percentage is the number that represents the proportion for each 100 objects. The whole is the reference quantity, and the percentage is being measured relative to this amount. The part represents the quantity that is in proportion to the whole. The multiplication by 100% is a conversion factor for converting a number into a percent. For example, suppose you tipped $5 on a $25 meal. In order to determine the tip percentage, you need to identify the variables in the formula. The $25 price tag for the meal is the quantity we're measuring the tip size against, so that is the whole. The tip is the quantity you're measuring relative to the cost of the meal, and that is your part. And the percentage is the number you're trying to determine. When working with this equation, you will need to know 2 out of the 3 quantities. From here, you can use algebra to solve for the third variable. Here are 2 other sample problems. The marketing budget for a company is $85,000. This quantity represents 5% of their total budget. How large is the company's total budget? You make a $632.74 purchase, and the sales tax rate is 8%. How much will you pay in sales tax? The key to solving these problems is to understand which numbers represent which values. What is the reference quantity? What is being measured against that quantity? What number is the percent? Once you understand this, it's just a matter of plugging the values into the equation and solving for the unknown. In class, we will look at a few more examples of this, including the idea of percent change. Suppose you wanted to buy something that costs $1,000, but you don't have $1,000 right now. What can you do? One option is to wait a few months so that you can save up the $1,000 and buy it then. Or you could buy it now by borrowing money. But instant gratification comes at a cost. In this case, that cost is called interest. There are lots of ways to structure loan arrangements. There are fixed and variable rate loans, loans with balloon payments, and some loans even have prepayment penalties. We will look at the simplest version, which is known as a simple interest loan. In a simple interest loan, you are borrowing a specific amount of money for a specific amount of time, and your interest is a specific quantity. Here's the formula for simple interest. Interest equals principal times rate times time. The interest is the actual cost of the loan. The principal is the amount of money being borrowed. The interest rate is the percent of the principal per year that you pay in interest. This is also known as the annual percentage rate, or APR. The time is the length of the loan in years, which is also called the term. The interest rate is the part that takes a bit of thinking to understand. It is a percent of the principal, which means that we're looking at a proportion of the principal. It seems to be clearly worse to pay a larger percent, so this suggests that a higher interest rate is bad, but it's not quite that simple. Since the annual interest rate is also a percent per year, this number is affected by the length of the loan. To understand this a little better, let's think through an example. Let's say you want to borrow $1,000 and you have a choice of 2 loan options. Option 1. It will cost you $100 to borrow the money and you have 2 years to pay it back. Option 2. It will cost you $150 to borrow the money and you will have 4 years to pay it back. Let's calculate the annual interest rate for both of these scenarios. We can see that option 1 has a higher interest rate than option 2, but the actual amount paid in interest is lower. The difference is in the amount of time that you have to pay back the loan. As you can see, even in the case of simple interest, it's not obvious how to determine whether one loan is better than another. The answer might depend on other factors that we haven't even considered, such as income and risk tolerance. Unlike what you might have thought about math previously, sometimes there's not a single right answer, and that's something you're going to want to get used to when it comes to mathematical reasoning. The ability to critically analyze a situation is much more important than merely the ability to calculate results. This has been a brief introduction to simple interest. In class, we'll be looking at compound interest, which happens when we start charging interest on the interest. A mortgage is a loan used for a piece of property. In this video, we're going to talk about some of the basics of a mortgage, including some of the terminology that is used when talking about mortgages. Purchasing a home is usually the largest single expense that people make, and it can be a very intimidating process. The reason that homes are bought with a mortgage is because very few people have the cash to buy a home outright. There are lots of reasons people buy homes, and each home buyer will need to weigh the risks and rewards of home ownership. At the same time, the bank also needs to weigh the risks and rewards of allowing someone to borrow a large amount of money from them in order to buy the home. If someone has shown themselves to be irresponsible with money in the past, such as carrying large amounts of credit card debt and not being able to pay them off, the bank will think twice about loaning them money. Let's say you want to buy a home. You will want to pay attention to both the term and the interest rate. Recall that the term of a loan is the amount of time in which you are expected to pay it back. Home loans are typically done with 15 or 30-year terms, although it's possible to have other terms. The interest is how much the bank is charging you to borrow their money. We are going to focus on fixed-rate loans, which are loans where the interest rate does not change. You can get a lower interest rate for a shorter mortgage, but your monthly payments will be larger. Typically, you would not take out a loan for the cost of the entire home. Instead, you would have a certain amount of money that you would pay up front. This is called a down payment. Having a down payment reduces the size of the loan that you need to take and also helps to demonstrate that you are financially responsible. Conventionally, the recommended size of the down payment has been at least 20% of the value of the house. However, in recent decades, that number has dropped quite a bit in some perspectives. But low down payments are a risk to banks because owners are less financially invested. Just before the recession, people were purchasing homes with no money down, and that contributed to the collapse of the housing market. When the buyer does not have 20% to put down, the banks are at an increased financial risk. In order to help mitigate this, the buyer must pay an extra amount for private mortgage insurance, or PMI. This amount only applies to the part of the loan that is beyond 80% of the price of the home. The PMI helps to protect banks in the event that you are unable to pay your mortgage. In other words, if you have less than a 20% down payment, you will pay an extra fee on top of what you already pay for the mortgage. This is another reason to try to have a larger down payment. As you can see, there are many components that go into figuring out the cost of a home loan, and there are even more things that we haven't even discussed here. The good news is that you can get reasonably good estimates using free online calculators. One such calculator can be found at mortgagecalculator.org. At the time of making this video, this is how the website looks. On the left side, there are boxes where you will type in various values. After entering the data, you will click the Calculate button. This will then update the information on the right. There's a lot of information here, and it can feel overwhelming. But this calculator will tell you the following important pieces of information: the size of your monthly payment with PMI, how much PMI you'll pay per month and for how long, and the size of your monthly payment without PMI. Although there is other information available, these are the basic numbers you'll be looking at if you get a mortgage to buy a home. In class, we will look at ways to try to determine whether you can actually afford to buy a home, as well as finding ways to reduce your payments. Have you ever heard people talk about how things used to be cheaper when they were younger?
Oh, don't poo-poo a nickel, Lisa. A nickel will buy you a steak and kidney pie, a cup of coffee, a slice of cheesecake, and a newsreel, with enough change left over to ride the trolley from Battery Park to the Polo Grounds.
This is not a matter of faulty memory. It's an economic reality. The costs of goods and services tends to increase over time. It takes quite a bit of knowledge of economics to really understand the forces that cause this to happen, so we won't get into the why of inflation. However, we can talk about various features of it. One way that inflation is measured is through the Consumer Price Index, or CPI. The most intuitive way to understand this is that the U.S. Bureau of Labor Statistics creates a list of goods and services that the average consumer purchases, and then measures how much it would cost to make those purchases. This list is called the CPI market basket, and you can imagine the CPI as measuring how much you spend at checkout to buy that basket of goods. It's actually a very detailed calculation that involves consumer surveys and complex mathematical models, and while there's a lot of interesting mathematics involved, they are not important for this course. What is important is how we can use the CPI to interpret inflation. The CPI uses the years 1982 to 1984 as the base for the calculation and sets this value to be 100. The CPI is calculated monthly. In January 2018, the CPI was 247.867. What this means is that if the CPI market basket would have cost $100 in the early 1980s, the exact same basket would cost $247 in 2018. In other words, you can buy less than half of what you used to be able to buy for the same amount of money. Because the value of the dollar is changing, when making these comparisons, we need to specify which dollars we're using. In the previous example, we would say that the basket costs $100 in 1982 dollars and $247 in 2018 dollars. The CPI can be used to estimate the value of money at different times by setting up a simple proportion. For example, suppose you won a $5,000 prize in January 1989. What is the equivalent to that prize in January 2012? The CPI was 121.1 in January 1989 and 226.665 in January 2012. The prize was measured in 1989 dollars. By solving for the remaining variable, we can see that the equivalent amount of money in 2012 is $9,358.59. Fortunately, the change of the value of money usually happens very slowly so that you do not feel the impact on a daily basis. There's no real difference in spending your money today and spending your money tomorrow. But what if that didn't happen? Imagine if you went to the store and a gallon of milk cost $2, but it only cost $1 yesterday. And tomorrow the cost is expected to rise to $5. Although this may sound absurd, this has actually happened many times in history. This is known as hyperinflation. How does this happen? One way it happens is if a government prints a whole lot of money all at once. Pretend you live in a small, isolated town, and everyone in that town suddenly won a $1 billion lottery. What do you think is going to happen? Initially, everything is extremely cheap. A $1 million home is suddenly very cheap. You can afford lots of them. How do you think this will impact the price of the house? Sellers will no longer accept $1 million for the home because they know they can sell it for much more. This is basically what happens with hyperinflation. Because there's suddenly a lot more money, people and companies will raise their prices rapidly in order to get the most value they can for their goods and services. Eventually, if this goes unchecked, the currency collapses because it's not really worth anything anymore. In class, we're going to look at the impact of inflation on savings and investments. Probability is the study of the likelihood of events happening when there's some form of randomness involved. Although we usually think of flipping coins and rolling dice, the concepts of probability are applicable to real-life situations, from setting insurance rates to predicting the spread of disease. We will begin our study of probability by learning some of the basic language and key concepts that we will need. In probability theory, an experiment is a repeatable procedure that results in a randomized outcome. This can be either a practical procedure, like dealing cards or drawing balls from an urn, or these can be hypothetical constructs, like modeling how long you wait in line at the grocery store. The important feature for us is that our experiments are repeatable. This means we can set up the same conditions over and over again and get consistently random results. The list of all possible outcomes of an experiment is known as the sample space. For example, if you roll a standard 6-sided die, there are 6 possible outcomes. We denote the sample space using set notation. It is important to use curly brackets to surround the list, and the items in the list are separated by commas. This will help with clarity and organization. An event is some collection of outcomes from the sample space. For example, when rolling a die, we can say that rolling an even number is an event. Events are also sets, so we must use set notation for these as well. We can also have events that have a single outcome, such as rolling a 1. If the die is perfectly fair, we would expect that the probability of each outcome is the same. When this happens, we say that the outcomes are equiprobable. And in this situation, it is easy to calculate the probability of an event. The left side represents the probability of event X. We can use different types of notation for X. We can state the event using words, or we can simply list the event as a set. This notation doesn't need to be technical, it just needs to be clear. A success is when the outcome is one of the events we are interested in. So a success of rolling an even number simply means that the outcome was either a 2, 4, or 6. This means that the probability of rolling an even number is 3/6 or 1/2, and the probability of rolling a 1 is 1/6. There will be times when we want to leave the probability as a fraction, and there will be times that we will want to convert it to a percent. It will usually depend on the context. To convert a fraction to a percent, you first must convert it to a decimal and then multiply by 100%, which is the conversion factor. In class, we're going to look at more complex probability scenarios and learn how to use probability trees to help us organize that information in an effective manner. When working with probabilities involving multiple random outcomes, it is important to understand the relationships between those outcomes. Two events are independent if one does not influence the outcome of the other. If you flip a coin and then roll a die, there's no reason to think that the outcome of the coin flip will impact the outcome of the die roll. However, if you deal 2 cards from a standard deck, the probabilities for the second card are influenced by the first card. If the first card is the ace of spades, then there's no way the second card could also be the ace of spades. We would call this dealing without replacement, and this is an example of dependent events. If we were to shuffle the ace back into the deck before dealing the second card, then the two events are now independent, and we call this dealing with replacement. We can use a probability tree to think about the nature of dependent and independent events. Suppose we have an urn that contains 2 blue balls and 2 red balls. Here are the probability trees for drawing with and without replacement. Notice that if we do not replace the ball, the probability trees for the second event are different. But if we do replace the ball, the probability trees are the same. The idea that some probabilities are connected to each other can sometimes play tricks on our brains. If you were flipping a coin and suddenly got heads 4 times in a row, you might feel that it's more likely that the next flip will be tails. Your intuition might be telling you that it's rare to see heads 5 times in a row, so you're due for a tails. Or your intuition might work the other way and you think you're on a hot streak. However, the reality of the next flip is that it is still a 50-50 proposition, just like every other coin flip. Another way of saying this is that sometimes our brain thinks that events are dependent even though they're not. This is known as the gambler's fallacy. We think that the probability of future events are impacted by previous events. In class, we will take a deeper look at dependent and independent events, and use that experience to take a look at the non-intuitive result known as the birthday paradox. Conditional probability can be a confusing topic. It is very important to pay attention to the details because the results can often go against our intuitions. If we were thinking about the chances of someone making a 3-point shot in basketball, our opinion would depend on whether the person is a professional NBA player or just a kid on the playground. Conditional probabilities work by limiting the sample space in some way, and then considering the probabilities of the restricted sample space. Recall that if all the events are equiprobable, then we can compute the probability of event X by taking the ratio of the number of successes to the number of possibilities. This is the formula for a conditional probability. The notation on the left is the probability that event X occurs given that event Y occurred. We can use the same principle for calculating the probability, but we only consider the cases where event Y occurred. Let's think about rolling a 6-sided die. What is the probability that the result is odd given that we rolled a number greater than 3? Our original sample space consists of the numbers 1 through 6, but there's an extra condition involved. We only care about the rolls where we had a number greater than 3. This means we have to get rid of the dice rolls that do not meet this condition. And now we can evaluate the probability and determine that the answer is 1/3. Here is the notation that we use. The event to the left of the vertical line defines success, and the event to the right of the vertical line is the condition that is placed on the sample space. There's another way to look at this formula. We can turn both the numerator and the denominator into probabilities by dividing both by the total number of possibilities. The numerator becomes the probability of both event x and y happening, and the denominator becomes the probability of y happening by itself. We can do this problem again with the new formula, and we see that we get the exact same result. There is another example, which is often called the boy-boy paradox. Suppose that a family has 2 children and one of them is a boy. What is the probability that the second child is also a boy? You'll have an opportunity to explore this question in the remainder of the pre-class activity. In class, we're going to look at an example of conditional probabilities in medical trials. Knowing that a test is 99% accurate doesn't always mean that you should be 99% confident in the result. When gambling, different probabilistic events are associated with a payout. Here are 2 hypothetical gambling games. Game 1. You roll a standard 6-sided die. You lose $1 if you roll 1 through 5, and win 1 cent if you roll a 6. Game 2. You roll a standard 6-sided die. You lose $1 if you roll 1 through 5, and win $1 million if you roll a 6. The chances of winning and losing are the same for each game, but you should be able to see that the first game is bad for you and the second game is good for you. You are intuitively picking up on the idea of the expected value of a game. There's more going on with this game than just the probability of winning and losing. Some wins are bigger than others. Here's the formula for expected value. There is a lot of mathematical notation, so we will break it down and do a couple examples. E of x is the expected value of game x. This is how much you expect to win or lose on average each time you play the game. This is known as the summation symbol. It is a shorthand notation for adding up several terms that all have a similar form. The variable I is known as the index, and it counts from 1 up to n. The value of n is the total number of outcomes. In this case, we will label all the outcomes x1, x2 up through xn. In general, you can use any notation you want for the outcomes as long as you've accounted for all of them. Just as before, P of xi is the probability of outcome xi. V of xi is the value of the outcome xi. In our example, this is the amount of money you win or lose in outcome xi. For the first game we discussed, there are 6 outcomes. We will let xi represent the outcome of rolling the number I and put all this information into a chart. When we expand out the summation notation, it looks like this. And then we substitute the probabilities and values for each of the outcomes, and it becomes this. Notice that losing money is a negative outcome, and winning money is a positive outcome. If we calculate this value, we get about negative 83 cents. How do we interpret this number? It means that on average, you will lose 83 cents every time you play this game. It doesn't mean that you will definitely lose 83 cents every time you play the game. But if you play the game a lot of times, you will find that on average, the amount of money you lose each game is 83 cents. If we switch to game 2, the only change is the value of rolling a 6. Instead of winning a penny, you win $1 million. When we do the calculation now, the expected value is about $160,000. This means that you expect to win around $160,000 every time you play the game. This is clearly a favorable game for you to play. In class, we will calculate the expected values of more complex games and use that to understand the house edge in casino games. Both probability and statistics are fields of study that involve a layer of randomness. For probability, we start with a model of a situation and try to determine information about the randomized outcomes. With statistics, we start with data that may have a level of randomness in it and try to determine a model that fits it. For example, if we're talking about flipping a coin, in probability theory, we might start with the idea that it is a fair coin that has a 50% chance of landing on each side. But with statistics, we would start by flipping the coin a bunch of times and ask whether it's reasonable that the coin is fair. When taking repeated measurements, we can create a frequency table. This is a table of all the outcomes that also displays how many times each result has happened. And once we've got these values, we can turn it into a chart. Charts like this are often called histograms or bar charts. This is a simple visual way to communicate information. Outcomes, such as heads or tails, and colors, are called categorical data. We are putting the outcomes into categories based on some characteristic. In some situations, the information we get is numerical. Numerical data give us other ways to try to describe the information. Suppose that we have an urn with balls in it, and each ball is labeled with a number. We don't know how many balls are in the urn, nor do we know what numbers they have, but we can reach in and grab a bunch of balls and just see what we get. We won't necessarily get all the balls, but we can use the information we have to make a guess as to what else is in the urn. Let's say we drew 10 balls and got the following collection. We can put this information into a frequency table and then into a chart. This gives us a quick sense of the data that we have. But there's more we can do. In fact, there are 3 specific numerical quantities that we can use to understand the numerical information: the mean, the median, and the mode. The mean is what most people think of when they think of an average. To calculate the mean, you add up all the values and divide by the number of values. The median is the middle number when all the values have been put in increasing order. If you have an even number of values, it's the average of the 2 middle values. In this case, the median is 2.5. The mode is the number that appears the most often. If there are multiple values that appear the most, then they are all considered to be the mode. Each of these values have important uses when trying to understand the data contained in the urn. They all try to give us a sense of what we should expect from the numbers coming out of the urn, but they all do it in slightly different ways. In class, we will look at some more examples of this to help build our experience and intuition for working with these values. The normal curve, also known as the bell-shaped curve, is one of the most important statistical distributions because of both its practical and theoretical significance. A lot of data can be approximated by these curves, and they arise naturally from certain types of calculations. We're going to focus on the qualitative aspects of normal curves in this video. Given a set of data, one of our goals might be to find the normal curve that best fits it. But before we can start trying to fit the data, we should take a look at the behaviors of the normal curve. This is what it looks like. It turns out that there are 2 parameters that we can change. One of those parameters is mu, which gives the location of the peak. As mu increases, the peak moves to the right. As mu decreases, the peak moves to the left. The value of mu turns out to be the mean of the data. The second parameter is sigma, which is a measure of the spread of the data. As sigma increases, the data is more spread out and the peak is lower. As sigma decreases, the data is much tighter and the peak gets much taller. Sigma is called the standard deviation. There is a formula for how to compute it, but we're going to stick with the qualitative description. If we return to our original dataset and correctly calculate the values of mu and sigma, we are able to overlay the normal curve on top of our dataset and see that we get a reasonable fit. It's not a perfect fit, but that's okay. It is rare that real-life data is ever a perfect match to a normal curve, but it turns out to be very close very often. The good news about mu and sigma is that we can use computers to calculate them easily. When working in Desmos, we can calculate the mean and standard deviation by using these functions. Simply type in the appropriate command, followed by the list of data points. The formulas are not particularly difficult to use, but it's rare that anyone ever calculates these numbers by hand. In a higher level course, we would use these formulas to help us derive more of our theory. But for this course, we will be focusing on the interpretation of these values, which we will do in class. There's one more value that's important to understand, which is known as the z-score. Let's focus on the normal curve where the mean is 10 and the standard deviation is 5. We're going to make markings along the x-axis using the standard deviation for spacing. A z-score is a number that we associate with every position along the x-axis. It measures how many standard deviations from the mean that position is. For example, if we look at the number 20, we can see that this is 2 standard deviations above the mean, and so the z-score for 20 is 2. The number 5 is 1 standard deviation below the mean, and so this has a z-score of -1. In class, we will see that z-scores can be used with a chart called a z-table to find out even more information about normally distributed data. Take a look at these 2 sequences of 20 coin tosses. One of them is the result of real coin tosses, and the other is a fake. Can you guess which one is which? At first, you might think they both look equally random, but it turns out that you can analyze these in a way that makes it seem very likely that one is random and seem very likely that the other is not. It's important that we say it seems random because it's impossible for us to tell with absolute certainty that one or the other is fake because both are possible random coin flips. To start to get a sense of how this works, let's look at a simpler problem. Let's say that your friend is flipping a coin. Their first flip is a head, and then their second flip is a head. At this point, everything seems normal. But then a third, fourth, and fifth head appear. As you start to see the sequence of heads grow longer and longer, you will start to get suspicious of your friend. Maybe they're being honest, but every time you see another head, it makes you question their honesty just a little bit more. But why would you do this? What is making you think that something is wrong? Our intuition tells us that this doesn't look like a randomized coin flip anymore. Getting 10 heads out of 10 flips just seems very unusual because it's so far from what we expect. We really only expect 5 heads in 10 flips. And that intuition is what starts us down the path of understanding how to detect fraud. Even though randomness doesn't have any patterns per se, we can know something about what to expect and recognize when things deviate away from that. Here are some examples of 10 coin flip patterns that don't seem to be random. In each case, there's some type of pattern that seems unrealistic if the result is supposed to be random. The regularity of patterns creates predictability, which feels a lot like the opposite of randomness. When trying to figure out whether there's randomness involved in the list, it's important that we have enough data to analyze. If we think back to our friend flipping all heads, there isn't anything suspicious after the first couple heads. It's only when you have enough information that you can start to say that there's a pattern developing. In preparation for class, you're going to need to come up with 2 lists of 75 coin tosses. 75 is a large number, but it's important that we have enough data to really be able to look for patterns. For one list, you're going to make it up on your own, but trying to do it in a way that looks random. For the other, you're going to use a random list of coin flips generated by a computer. This can be done by going to random.org and using their virtual coin flipper. In class, we're going to see whether we can tell the difference between the faked random list and the truly random list. As important as it is to have lots of data, it can also be dangerous and deceptive. As you get more data, it becomes more likely that you will find a pattern that's a result of randomness. The probability of flipping 10 heads in a row is 1 in 1,024. This means that if someone flips a coin 10 times in a row, you would expect that 1 time out of 1,024 will end up with 10 heads in a row simply by chance. What happens if we have thousands of people flip a coin 10 times in a row? With enough people, you would expect to find that someone has flipped 10 heads in a row. But now let's focus on the person that got the 10 heads in a row. Does it make sense to look at them and say that they must have cheated simply because they got 10 heads in a row? If we were only watching this one person, we might be suspicious. But in the larger context of having thousands of people do this experiment, it doesn't seem suspicious at all. In fact, it's expected. So when we're looking for fraud, we need to be very careful in our approach. The rest of the pre-class activities will show you a few more ideas in fraud detection, such as Benford's law. And in class, we will analyze the real and fake coin flips to see if we can discover accidental patterns in the fake data.